In April 2025, a facility in California squeezed a peppercorn-sized pellet with the world's biggest laser and got 8.6 megajoules of fusion energy out. A record. Headlines screamed net energy, but the building didn't power itself. The lasers drew roughly 300 megajoules from the grid. The experiment didn't produce net energy. It just broke even relative to the beam that hit the target. That difference is everything. This is the story of why igniting a star in a lab is a monumental feat and why we are still a long, long way from a fusion power plant. 2 machines, 2 approaches, and the brutal engineering that stands between us and unlimited clean energy. So what did they actually do? The National Ignition Facility, NIF, fired 192 laser beams into a tiny gold cylinder. Inside that cylinder, a diamond capsule the size of a peppercorn. Inside that capsule, a frozen mix of deuterium and tritium. The lasers hit the gold, which blasted X-rays onto the capsule, causing the capsule to implode the fuel. For about a billionth of a second, the center of that pellet became the hottest place in the solar system. Peak power hit 456 terawatts. That's about over 60 times the entire world's electrical generating capacity. Focused on a peppercorn for an instant, and the fusion reaction spat out 8.6 megajoules of energy. The laser energy that hit the target was 2.08 megajoules. So the target gain, fusion out over laser in, was 4.13. That's scientific breakeven. The fusion reaction gave more energy than the laser delivered to the fuel. Congratulations, physics works. But here's the catch. The lasers didn't just appear. They were pumped by massive flash lamps. Those flash lamps ate electricity from the grid. The whole facility, capacitors, cooling, amplifiers, diagnostics, consumed around 300 to 400 megajoules per shot. So for every unit of fusion energy out, the building sucked in roughly 40 units of electricity. That's engineering breakeven. Or rather, not breakeven. Not even close. Scientific breakeven is lighting a match. Engineering breakeven is using that match to power your house. NIF lit the match. The house is still on grid power. Think of it like a toaster. A toaster pulls about a kilowatt. To use 300 megajoules, you'd have to run that toaster for 300,000 seconds. That's over 3 days of continuous toast. And what did we get back? 8.6 megajoules. That's about enough to run the same toaster for 2.5 hours. You toasted for 3 days to get enough energy to make toast for a couple of hours. That's the gap. Why is the laser so inefficient? NIF's lasers are 1990s technology. They use neodymium-doped glass slabs pumped by xenon flash lamps. Most of the electrical energy becomes heat, not laser light. The laser efficiency is about 1%. That means for every 100 joules you pull from the wall, about 1 joule ends up on the target. The other 99 joules warm up the building. There are better lasers now. Solid-state diodes, more efficient. But NIF was built before those were ready. Upgrading is possible. The Department of Energy approved a project to boost laser energy to 2.6 megajoules. That might push fusion output to 30 megajoules. Still a net loss. Still your toaster runs longer than the fusion burn. And you still need to run it for days to get there. Okay, so one shot doesn't cut it. What if we just fire the laser over and over? That's the repetition rate problem. A power plant needs to fire about 10 shots per second. 10 times a second, a new fuel pellet must be injected, positioned with micron precision, and blasted. NIF fires about once a day, sometimes less. The lasers need to cool. The optics need to be checked. The target chamber needs to be pumped back to vacuum. The fuel pellet is hand-assembled, a tiny engineering marvel that costs more than a car. You need a factory that spits out these pellets like soda cans, 10 per second, for years, without jamming. And you need a laser that can fire 10 times a second without melting. NIF's laser is a sledgehammer. You need a sewing machine, fast, precise, and relentless. That machine does not exist. But NIF isn't the only game in town. Over in France, they're building a different beast. ITER, a tokamak, a magnetic donut. Instead of crushing a pellet with lasers, ITER will use giant superconducting magnets to hold a hot plasma in place. The plasma, a swirling cloud of deuterium and tritium, gets heated to 150 million degrees, hotter than the core of the sun. The magnets keep it from touching the walls. The goal is to sustain a fusion burn for hundreds of seconds with a gain of 10. 500 megawatts of fusion power from 50 megawatts of heating. That's Q equals 10. Scientific breakeven for magnetic fusion. But ITER is also a research reactor. It will not generate electricity. It will not breed its own tritium fuel. It will just prove that a burning plasma can be controlled. And it's been under construction since 2007. It might start experiments in the 2030s. Maybe. Both approaches, inertial and magnetic, solve the physics. Then they run into the same wall. Materials, neutrons, tritium. Heat. The fusion reaction spits out a neutron with 14 megaelectronvolts of energy. That neutron slams into the reactor wall. Over and over. It knocks atoms out of place, makes the metal brittle, makes it swell, makes it radioactive. A commercial reactor would have to survive this neutron storm for years. We don't have a material that can do that. We have candidates. We test them in small reactors and particle accelerators. But nobody has run a fusion reactor long enough to see what really happens. It's like trying to design a bridge without knowing what rust is. You can guess, you can simulate, but until you build it and leave it in the rain, you don't know. Then there's tritium. Deuterium you can extract from seawater. Tritium is radioactive. Half-life of 12 years. Almost none exists naturally. You have to breed it. Wrap the reactor in a blanket of lithium. When the fusion neutron hits the lithium, it makes tritium. Then you collect that tritium and feed it back into the reactor. This is a fuel cycle that has never been demonstrated at scale. If you can't breed more tritium than you burn, the reactor starves. It's a weird fuel cycle. You burn the fuel, you make more fuel in the walls, you hope you make slightly more than you burned, and you do this continuously. It's like a car that has to refine its own gasoline while driving. We're not there yet. And now the question you've been waiting for. Isn't fusion basically a hydrogen bomb? No, a hydrogen bomb uses a fission trigger, a small atomic bomb, to compress and heat fusion fuel to insane conditions. It's an explosion designed to be as big as possible. A fusion reactor uses a tiny amount of fuel, milligrams. If anything goes wrong, the plasma touches the wall and cools instantly. The reaction stops. There is no chain reaction, no meltdown. The challenge is keeping the fire lit, not stopping it from spreading. Fusion is a campfire that refuses to stay lit. A bomb is a campfire that becomes the entire forest. They share some physics, but not the engineering, not the scale, and not the outcome. You can sleep next to a fusion reactor. You cannot sleep next to a bomb. So where does this leave us? The headline said fusion finally worked. It did, in the same way the Wright brothers' first flight worked. A monumental achievement, a proof of principle. But a 12-second hop over sand is not a transatlantic airliner. NIF's 8.6 megajoules is a 12-second hop. Turning that into a power plant means solving the repetition rate, the laser efficiency, the materials, the tritium breeding, the heat extraction, and the economics. All at the same time. The DOE's roadmap pushes for a pilot plant maybe in the 2040s. Private fusion companies say 2030s. They always say 2030s. It's a magical decade where all problems are solved. Most scientists think commercial fusion, if it happens, is a 2050s thing. Maybe later, maybe much later. Think of it this way. We proved fusion works. Now we have to build a machine that can do it 10 times a second, breed its own fuel, survive a constant neutron sandblaster, and produce electricity cheaper than solar, wind, and batteries combined. That's not a physics problem. That's an engineering marathon. In the rain, uphill, with a toaster strapped to your back. And the toaster is melting. The 8.6 megajoule shot is a glimpse. a glimpse of a star in a bottle, a testament to human cleverness and precision. But don't hold your breath for fusion-powered toasters. We lit the match. The furnace is still a blueprint. The road is long, the problems are hard, and nobody knows when we'll get there. But we're walking. That's the real story, not net energy, not unlimited power tomorrow. Just a bunch of engineers staring at a peppercorn-sized sun and asking, how do we do that again, but faster and cheaper and forever? Good luck to them. They'll need it. And so will your toaster.